Hi, my name is Dr. Avril Slaughter, and welcome to this course on how to make your Wi-Fi network stable and fast in a home or in a small office environment. I have been working on Wi-Fi networks since the late 90s, early 2000, when the Wi-Fi networks were first being defined and implemented. And I teach leading organizations not only about the technology itself, but also how to overcome some of the many deployment challenges. And invariably, when I start talking about Wi-Fi networks, people ask about problems that they're getting in their home networks. So this video training is specifically for people that are struggling with getting the best out of their Wi-Fi networks at home. And it's going to talk about the 5 most common issues, and it's going to talk about the 5 things that you can do to improve your Wi-Fi networks at home. And it will show you not only what you can do, but explain to you why that's going to make a difference. I always think it's nice if you can see a little bit about the person who's imparting information to you. And so this is a picture of me in the Microsoft studios up in Redmond in Washington a few years back when I was doing Windows 7 training for Microsoft's partners. The first thing we're going to talk about is your Wi-Fi router. And we're going to talk about what frequency band it operates on, and whether you acquired a single band, a dual band, or a tri-band Wi-Fi router, and what the implications is of acquiring those different products. Your Wi-Fi product will be operating in either the 2.4 or the 5 gigahertz band, or both. What is the implications of connecting in those different frequency bands? Once we have an understanding of your Wi-Fi router and the frequency band is deployed in and its implications, we need to talk about where you installed your Wi-Fi router. What is its location in your home? Where you deploy Wi-Fi can make a major difference to your Wi-Fi experience. And I'm going to show you a few simple things that you might be able to do to improve how Wi-Fi is working for you in your home. We then want to talk about the settings that you have defined for your Wi-Fi router. Some of you may have just left it, just plugged it in and connected to it and never changed any of the settings. But I suspect most of you would have at least given it a name and set up a password to secure access to your home Wi-Fi router. Some of you may have even gone ahead and defined things like the channel that you want your Wi-Fi router to operate on. I'm going to touch on some of those router settings so you can understand what the implications are, and I'll give you a couple of recommendations that hopefully will help your Wi-Fi network performance. Next, we want to talk about what are the data rates that you're able to achieve on your Wi-Fi network. Many of you today will have an agreement with your internet provider, and they may be providing something like 50 megabits per second speeds to your home. And some of you may know how to go into your browser and run a speed test to check that you're actually achieving those data rates. We want to take a look at what data rates you're achieving over your Wi-Fi network and help you understand some techniques that can improve your Wi-Fi experience in the home. And the last very common area I get questions on is, will extenders, Wi-Fi repeaters, can I put high gain antennas on my access point? How do they affect things, and will they fix my problem and make Wi-Fi perform better? So we're going to talk about that in our last section. The first thing we want to talk about is your Wi-Fi router and what frequency band it operates on. When you think about Wi-Fi, it operates on different frequency bands, and this is no different to your car radio. Your car radio, for instance, operates on FM and AM, and these are simply different frequency bands, and when you turn the dial, you're just basically selecting a different frequency. And what you're doing is you're tuning in to the frequency that your favorite station is being broadcasted on. For example, I like to listen to the BBC World News, and so I turn my dial to the Pacific frequency where I can then listen to the BBC News. Whereas AM operates in the kilohertz channel and FM operates in the megahertz channel, Wi-Fi networks operate at much higher frequencies, up in the gigahertz bands. There are many technologies that operate up in these higher frequency bands. In addition to Wi-Fi, this is where you'll find your mobile cellular networks. This is where you'll find Bluetooth, cordless phones, and other devices. If you have a Wi-Fi router that is a single band, what that means is it operates in the 2.4 gigahertz band only. If it's a dual band Wi-Fi router, that typically means that it has two radios in it and is capable of operating simultaneously in both the 2.4 and the 5 gigahertz band. If you're fortunate enough to have a tri-band Wi-Fi router, then that means it has three radios in it and is capable of one radio operating in the 2.4 gigahertz band, and the other two radios can simultaneously communicate in the 5 gigahertz band, giving you three radios in total. If you have an access point that's capable of transmitting both in the 2.4 and the 5 gigahertz band, then when your device goes to connect, it needs to choose which frequency band it wants to connect to. Does it connect on the 2.4 or does it connect on the 5 gigahertz band? Your device will make this decision based on how well it can hear the signal in the 2.4 gigahertz band or in the 5 gigahertz band, and it will connect to the signal that it can hear the strongest. And if everything else is the same, the signal that is going to hear the strongest is going to be the signal that's transmitted in the 2.4 gigahertz band. In other words, your device will connect to the 2.4 gigahertz band and not to the 5 gigahertz band. Wi-Fi operates the same way, whether it's a laptop, a smartphone, or a tablet, desktop, etc. So what that means is that all of your devices will connect on the 2.4 and not the 5 gigahertz band. And all of your neighbor devices operate the same way, i.e. if your neighbors have deployed single or dual mode or tri-mode access points, most likely their devices will be connected on the 2.4 gigahertz band and not the 5 gigahertz band. What this means is that your 2.4 gigahertz band is going to have a lot of traffic on it, and it's going to be really crowded. And just like when you drive home in rush hour, it's going to take you a long time to get anywhere. In other words, if you're watching videos or surfing the web, you're going to notice delays if you're operating in the 2.4 gigahertz band, whereas the 5 gigahertz band is relatively clear. So the question becomes, how do you make sure that you connect on the 5 gig, which is relatively clear, in comparison with connecting on the 2.4? The way we make our client connect to the 5 gigahertz band is simply to give different names for the network that's operating in the 2.4 gigahertz band than the network that's operating in the 5 gigahertz band. In other words, I go into the settings on my wireless router and I give it a network name such as Avril's Network 2 for the network operating in the 2.4, and I give the name of Avril Network 5 for the network operating in the 5 gigahertz band. When I bring up my client and it asks me what network do I want to connect to, I will therefore have two networks displayed, both Avril Network 2 and Avril Network 5, and I can go ahead and select Avril Network 5, in which case I'm going to connect to that network and therefore operate in the 5 gigahertz band. Now, most of you probably don't have the same Wi-Fi router as myself. So what you need to do is you need to connect to your Wi-Fi router as an administrator and get into your settings. Normally when you get into your Wi-Fi router, you would select, just like I did here, wireless settings. And to change the network name, that's normally a very fundamental feature. And so on my Wi-Fi router, on my wireless router, is under basic security settings. And here it says I can change the SSID. And you can see it's even given me a description to say that the SSID is the same as the network name. On your wireless router, it may just be called network name. And you can see that I can have a different name in the 2.4 than I can for the 5 gigahertz radio. And so I've simply gone in and put the name of Avril Network 2 for the 2.4 gigahertz band and Avril Network 5 for the 5 gigahertz band. And I on purposely used 2 and 5 because then I can remember which frequency bands they are. I can then go ahead and save those settings. Now when I go to connect my laptop or smartphone or tablet and I look to see what networks are available, I will be able to select Avril's Network 5 and therefore connect on the 5 gigahertz band. By configuring your 5 gigahertz network with a different name and then forcing your devices to connect to the 5 gigahertz band, you're no longer going to be competing for resources with your surrounding neighbors that are using the 2.4 gigahertz band. And this can have a significant improvement, and because of this, you can have a significant improvement in the performance of your Wi-Fi network. Now you might be saying, well, what about if my neighbors work this out as well and also change their network names to be different on the 2.4 and the 5 gigahertz band and then also connect their devices on the 5 gigahertz band? Then as those users get smarter and start to leverage off the 5 gigahertz band, then again you will be competing for resources in that frequency band. However, there is some very good news. And that good news is that there's a lot more spectrum available in the 5 gigahertz band for you to share with your neighbors than is available in the 2.4 gigahertz band. And it's because of this availability of spectrum in the 5 gigahertz band that some vendors have produced tri-band wireless routers, which then have 2 radios that can both simultaneously operate in the 5 gigahertz band. Now, if you have 2 radios in the 5 gigahertz band, you can give them 2 different network names. And that's what I've done here. I've added an extra network name called Avril's Network 5 TV. And the reason I'm calling it TV is because I'm going to use that radio just for connecting my TV where I want to experience the best data rates in order to get the best video experience. Any other devices that I've got in my home, such as if I want to be playing gaming, surfing the web, etc., I'll do on Avril's Network 5. The last thing I do in my household is I put all the children and the visitors on Avril's Network 2, so that way my traffic on Avril's Network 5 and 5 TV is not impacted because of the traffic being generated by my children or visitors. This was our first module on how to improve Wi-Fi in your home or small business environment. We were focusing on understanding the frequency bands that are available for you to connect to and send your traffic. Thank you for watching this module. In this module, we're going to talk about the things that can affect the performance of your wireless network that relate to how you position and locate your Wi-Fi router. Now, as I go through this module, there'll be some things that you say, well, that might make it better, but I can't do it, and that's fine. And there'll be some things where you'll go, well, that's an easy thing to do. Let me go fix that now. So as I go through this, don't think you have to do everything in this module, although if you did, you would certainly improve the performance of your wireless network. The first thing to note is that your access point will radiate signals out almost in a circular pattern. In some people's homes, they deploy their wireless router close to where the cable or DSL connection comes into the home, and quite often that could be on the peripheral of the home. And you can see that if the access point is radiating equally in all directions, that this will somewhat limit the areas that you might be able to get connectivity to that wireless router. To maximize your coverage in a home, ideally, therefore, you want to locate your wireless router in a center location within the home. Now, sometimes this may be problematic because you may not have power that you're able to run to the access point at that location, or you may think that it's not cosmetically appealing to have the wireless router in the middle of the home. Nevertheless, the center of the home is normally the ideal location to maximize coverage within your home. In some people's homes, all the wiring comes into a closet area or the laundry room, and so they place the wireless router in that location. If you place a router in a closet, particularly if you've got other equipment in there, what you're going to find is that you'll lose signal strength, because your signal will lose power as it goes through the walls and the door. How much your coverage is reduced by depends on the construction of the wall and how many other obstacles there are in the closet. This is an example of a planned deployment in my friend's home. We plan to put it up here on the beam. It's in a center location in the home. It's going to be fairly inintrusive, but up here on the beam you can see that it's fairly close to where lights are running, so it's going to be possible to get up in the roof and to run power and also run a network cable. We'll be looking for a white wireless router, so it doesn't look any different from what you might expect already on your walls or ceilings. For example, your light fittings, maybe you have a door chime for when people knock on your doors, or maybe you have speakers in your ceiling. This of course does require installation work, but you will be rewarded with better coverage and better performance. Another critical consideration for locating your access point is to raise it up off the ground to get it as high as possible. This will prevent signals being disrupted or blocked by things like furniture. For example, if you don't want to mount your access point on the wall or the ceiling, putting it up on top of a high cupboard or bookshelf will improve your coverage and your performance. Many wireless routers today have advanced features such as beam forming that use multiple antennas for both transmitting and receiving signals. These antennas are simple omnidirectional antennas like I'm showing here, which we sometimes call rubber duckies or whip antennas. When the signal radiates out from these antennas, it doesn't radiate equally in all directions, but it rather forms this donut type shape where the signal is stronger as it radiates to the side of the antenna than it does radiate up or down from the antenna shown in this picture. What that means is when you deploy your wireless router in your home, if you have external antennas, you need to make sure that they are upright in order to maximize the coverage across your home. If your antennas are down tilted, which often can be the case when they just get knocked, and what's going to happen is it's going to change how the signals are propagated. And in this illustration you can see I've put my antenna horizontal, and now my signal is going to radiate more towards the roof and to the floor and less to the sides of the house in this illustration. So unless you want coverage on the roof, then you should look to keeping your antennas in a vertical position. The last thing I want to talk about in this module when it comes to thinking about where to position your wireless router is reflective surfaces. So you may be aware that behind the glass of a mirror is a coating of silver, and it's that silver that reflects the light, such that you can see an image, such as in this picture here. Your radio signals are just like light, and they can also bounce off highly reflective surfaces such as your mirrors and any other metal objects in your home. You can think of your radio signals traveling in waveforms, just as light travels in waveforms. If that waveform reflects off a surface, then these waveforms can be combined. And in this first illustration, the waveforms are actually reinforcing each other and strengthening the waveform. When that happens, you actually receive a stronger signal. But conversely, a reflective signal could be combined with other signals to actually cancel the signal out. What this means is if you deploy your wireless router close to highly reflective surfaces, you could find some areas where the signal is stronger and other areas where the signal has been cancelled and causing a deep fade. You may have experienced this effect when you're driving and you've stopped at the lights and you are listening to your favorite radio station, but there's a lot of disruption of the signal, and so you move your car forward a little bit closer towards the lights, and then all of a sudden you're able to hear your radio station clearly again. What you've done here is you've taken yourself out of a fade condition where you were losing the signal into an environment where you can now hear the signal clearly. Therefore, it's recommended that when you deploy your wireless router in your home, you do not deploy it too closely to highly reflective surfaces such as mirrors and metal objects. We have been talking about how to improve the performance of your wireless network in your home or small business environment. And in this particular module, we were talking about the implication of where you locate your wireless router relative to performance. I hope you enjoyed this video. I also hope that you will make some changes to your wireless router deployment in order to reap the benefits of an improved network. Thank you for watching. In this module, I want to talk about some of the settings that are on your wireless router that you might want to look at and consider changing in order to improve the performance of your wireless network. There are many different wireless routers out there, and different vendors have different interfaces for you to set the settings on those devices. So when I take you through these settings, it may be possible that you're able to change the settings. It may be that you can't change those settings on your device. It may be the settings are called the same name that I'm going to use in this session, or they may have a slightly different name. So in this section, I'm not going to show you how to change these settings. I'm more going to talk about the settings you should look at and understand and how they will impact performance of your wireless network. Once you understand what the settings are capable of doing, you can then pull the user guide for your device and see if it's something that you can actually change in the wireless router that you are currently using. So with that understanding, let's begin. In an earlier module, you saw how I changed the name of the radio that was operating on the 2.4 GHz band to Avrils Network 2, and the radio that's operating on the 5 GHz band to Avrils Network 5. And we did that so that when I connect to my wireless network, I can ensure that I'm connecting to the frequency band that I prefer. Let's now take a closer look at these frequency bands. Let's start by looking at the 2.4 GHz band. And I thought, rather than showing you a slide, why don't we actually take a look at the frequency itself so you can actually see what's going on. Along the bottom here, you can see the frequencies in the 2.4 GHz band. Now the frequencies are written in megahertz. So 2405 here is the frequency in megahertz. If you were to say that in gigahertz, it would be 2.405. And you can see the frequencies go up in increments of 5 all the way to the top part of the band. Wi-Fi then defines channels that will operate on specific frequencies. If I change the view here from saying let's not look at frequencies but let's look at the Wi-Fi channels, then this changes it from the frequency band now to the channels that are defined in the Wi-Fi specifications. And you can see channel 1, channel 2, channel 3, etc. And these channels are separated by 5 megahertz. Let's now go and take a look and see if we have any access points operating on these channels. And to do that, I'm just going to slightly change the display so we can see the networks that I can hear. I'm going to sort it based on channel number, and here we can see that I have some access points being broadcasted on channel 1. So let's click on this one and get it displayed, and you can see that it is indeed being transmitted on channel 1, and you can see that when it transmits it occupies a chunk of the spectrum. Now I also happen to have an access point here on channel 2, so if I click on that one you can see that these are overlapping, and if they overlap they're going to interfere with each other. So typically what we want to do, if I turn off channel 2, typically what we want to do is we want to deploy our access points on channel 16 and channel 11 because these channels do not overlap with each other and therefore do not interfere with each other. If you deploy access points on any other channel, so for example I can see here some on channel 8, some on channel 9, I've got some on channel 4 and channel 2, these will overlap with each other and cause interference. Ideally, you really want all the Wi-Fi networks in the 2.4 gigahertz band to be operating on channel 1, 6 and 11, which are non-overlapping. But as you can see, you often see access points deployed on overlapping channels. And the reason that is because most wireless routers today have the channel selection set as automatic. What they're meant to do is to listen over the air and determine the channel with less interference and noise on it, and then select that channel for operations for that wireless router. Unfortunately, it doesn't work really well, and more often than not, you'll have a channel assigned that is actually more problematic. And therefore I would recommend that if your access point is set up to automatically select a channel, to put it back to manual assignment. So let's take a look at how I would do that on my wireless router. But remember, it may be in a different location on your device and you may have to hunt around for it. So for this particular wireless router, it's under basic security settings, even though this has nothing to do with security. And if you remember, this is where I was earlier when I changed the name of the SSID, when I changed the name of the network. And right underneath that, you can see both the 2.4 and the 5 gigahertz bands have been set up as automatic. I'm going to take this one and I'm going to change it. And I'm going to select either channel 1, 6 or 11. Now with my tool I'm able to tell how many access points around me are on channel 1, 6 and 11 and how much noise and interference they're making, so I can select the channel that's less noisy. Most people for their home network would not invest in such a tool, and therefore you don't really know whether to try 1, 6 or 11. And what I'd recommend is you just try them, and you try it at the busiest time of day, which is normally in a home network somewhere between 6 and 8 o'clock at night, and just try the different channels and see if you notice a difference in performance. In my case, I'm going to select channel 11. I'm just going to show you what the selections are for channel 5 on this particular access point, and you'll notice that there are 9 different channels that I can select from. So let's now talk about those channels and why I only have 9 that I can select. When we look at the 5 gigahertz band, there are many more channels available on which you can transmit your wireless signals. And here you can see 25 channels in comparison with 3 that we were looking at in the 2.4 gigahertz band. In 802.11n, you can aggregate two 20 megahertz channels together to form a 40 megahertz channel. Doubling the bandwidth doubles the data rate. And so 802.11n gets you up to higher data rates, in part because of going to these wider bandwidths. 802.11ac allows you to aggregate even more 20 megahertz channels. And in AC, you can aggregate 4 20 megahertz channels to get to an 80 megahertz channel. And some of the newer products, you can aggregate 8 20 megahertz channels together to get a 160 megahertz channel. And again, whenever you increase the channel bandwidth, then you're going to increase the data rates that you can achieve over the air. What's important for you to understand is not just the channel numbers and the bandwidth, but is to understand that the 5 gigahertz band is actually broken up into 4 chunks called the Uni 1, the Uni 2A, the Uni 2C, and the Uni 3. And the regulatory rules are different for different chunks of spectrum. And in particular, any radio that's operating in the Uni 2A or the Uni 2C bands must avoid interference with primary uses of that band, such as radar systems and satellite systems. These bands therefore mandate that the wireless router must do dynamic frequency selection and transmit power control. Dynamic frequency selection is where the wireless router will identify that there's other traffic on the frequency band and then take action to avoid interference with those other transmissions. And how does it avoid interference? It dynamically moves to a different frequency channel. Transmit power control is when the wireless router will automatically ensure that both itself and clients adjust its transmission power levels to minimize the interference that they're causing with other technologies that are transmitting in those bands. Now, it's not so important that you know what these technologies are. What's important to understand is that the Uni 2A and Uni 2C require those technologies to be implemented in your wireless router. Those wireless routers, therefore, tend to be a little bit more expensive, and consumer-grade wireless routers like you and I have deployed in our homes typically do not have these capabilities and therefore will not operate on the Uni 2A and the Uni 2C and will operate on the Uni 1 and the Uni 3 bands only. And hence why you saw in my access point, for example, that I could only select channels 36 to 48 and 149 to 165, i.e. the Uni 1 and the Uni 3 bands. If you are fortunate enough to have an access point that operates in the Uni 2A and the Uni 2C in addition to the Uni 1 and Uni 3, then I would recommend that you do not put your channel selection on automatic, but rather you choose one of the channels in the Uni 2A or the Uni 2C. The reason is that most consumers, i.e. your neighbors, will be on the Uni 1 and the Uni 3, and the Uni 2 and the Uni 2A and the Uni 2C will therefore be relatively clear from interference from other wireless LANs. Now, before we move off the frequency plans, I do want to make sure that you know that this diagram here showing the 5 gigahertz band, as noted in the bottom right hand corner, is the North America channel plan. These terms, Uni 1, Uni 2, Uni 3, are terms that are used in the United States. They're not terms that are used in Europe or in Asia. So if you're watching this and you are not in the United States, then your frequency bands are going to be different. For example, the frequency bands here are very similar in Europe, even though they're called something different, except that you don't have the Uni 3 band in Europe. In countries like China and India, there's even less spectrum available to be used in the 5 gigahertz band. So let's now go on and talk about the last configuration option that you might want to consider to improve your performance of your wireless network at home. And that's something called the mode of operation. And technically there's a greenfield mode and then a mixed mode. What does that mean? Well, in a greenfield mode, that means you're just supporting the new radio and you're no longer supporting legacy equipment. In a mixed mode environment, you're supporting the newer radio, but you're also supporting the legacy radio. Unless you still need to support older equipment, let's say you've got an old laptop which is only 802.11b, or a tablet that you've had for some time and only supports 802.11g, then you'll need to operate in a mixed mode of operation. But if you don't have legacy equipment, then you should move to a greenfield mode. And this can give you anywhere between a 5 and to a 15, if not 35% performance improvement of your wireless network. So to help you understand this, I brought up my router again, and under Advanced Security Settings in my access point, I have this setting called 802.11bgn-AC mode. And this is what we want to click on if we don't have legacy equipment. So let's select that. And you can see here that in the 2.4 gigahertz band, I'm supporting B and G radios. And what I'm going to do is I'm going to switch to 802.11n only, because everything in my home network is now N or AC. And here in the 5 gigahertz band, your options are normally to support A, N, and AC, and you want to switch to N and AC. And if you only have AC equipment, then by all means you can switch to AC only. I'm going to leave it as N and AC mode because I do have N equipment in my network. This will give me a significant improvement in the 2.4 because I'm now no longer allowing B and G devices to connect. I'm going to click apply, and that will then save those settings. In this module, we talked about some of the settings that you can change in your wireless router that will improve the performance of your wireless network. We referred back to setting up different SSIDs for the different frequency bands. We then talked about the channels and the channel numbers, both in the 2.4 and the 5 gigahertz band. And we just finished up talking about moving from a mixed mode of operation where you're supporting legacy equipment to a greenfield mode of operation where you turn off support for your legacy equipment, your 802.11b, A, and G radios, and that will give you between 5 and 35% improvement as well. I hope you found this module useful. On the next one, we're going to talk about data rates. Thank you for watching. One of the biggest issues people have with a wireless network is an expectation of what kind of data rates that they should be experiencing when they're sending their data over the air. And so in this module, I want to explain to you what those data rates mean when they talk about the product getting up to 300 megabits per second or 1 gigabit per second. What does that really mean? And I'm going to talk about how you can maximize the data rate that you're getting in your wireless network. So let's get going. This is a product that I acquired some years ago, and you can see that it states that it's 802.11n and is able to achieve data rates of 150 megabits per second. So what we want to talk about is, what does this mean when it says I can achieve data rates of 150 megabits per second? The first thing you need to understand is that data rates vary as you move around. So if you're close to the access point in really good RF environment, then your data rates are going to be the highest. As you move away from the access point into more difficult RF environment, then your data rates are going to drop. And as you keep moving, your data rates will continue to drop until you're on the edge of cell coverage. And at this point, you will experience the lowest data rates. Of course, if you continue to move, then you'll be outside of coverage and you won't be able to connect at all. What this means is that if you want to achieve the highest data rates possible in your wireless network, then ideally you want to be located close to the wireless router. If you need high-speed wireless connection in one specific area of your home, perhaps for instance a home office, or perhaps you watch internet TV, so you want it close to where your media equipment is, then deploying your wireless router close or within your home office or close or within your media center will improve your data rate experience. Now, to understand what data rate you can achieve when you're in good RF environments, such as close to the access point, not moving very much, versus what you can achieve in more difficult RF environments, such as on the cell edge, then you need to understand these data rates that are described on your product's packaging. Typically, and when I say typically, I can't think of one example where this has not been the case, but the data rates that you see advertised for your product will be the maximum data rates that are achievable if you're in good RF conditions. In other words, this product we're looking here, the maximum possible data rate you can achieve is 150 megabits per second. If you move to the edge of the cell, your data rates will drop. And in the case of this product, 802.11n, it'll drop down to about 6 megabits per second on the edge of cell coverage. So if we go back to my TCP link nano router that I acquired some years ago, what that 150 megabits per second is telling me is that if I'm in good RF conditions, I can expect to get 150 megabits per second. What it's not telling me is that my data rates will drop as I move away, and if I'm on the edge of coverage for this device, then my data rates will drop to just a little over 6 megabits per second. So let's say you've just gone out and you've bought yourself a brand new 802.11 AC router. It's got, in this example, 8 antennas, is supporting advanced features like multi-use MIMO. Then what that's saying to you is that if your device is capable of also having sufficient antennas, also has 802.11 AC, also supports multi-use MIMO, then under those conditions, if you're in really good RF environment, you can get up to over 2 gigabits per second. And just like with my little nano router, if you move to the edge of the cell, your data rates will also drop, potentially again dropping all the way down to data rates as low as 6 megabits per second. So it's really important to understand that you can get these data rates if your clients support all of these advanced features and you're in perfect RF conditions. If your client does not support those advanced features and you're not in good RF environment, then you won't be able to achieve that over-the-air data rate. For example, let's say you have a small tablet that only has one antenna and does not have 4 antennas for transmitting and receiving, then the maximum data rate that you can achieve on that tablet in good RF environments is 1/4 of that advertised data rate, and your data rates will actually be closer to 540 megabits per second. Again, that's assuming a good RF environment. If you move to the edge of the cell, again, your data rates will drop all the way down to 6 megabits per second. If you remember earlier, we talked about how your wireless router maybe have 1, 2, or 3 radios in it. And in this picture, I've got 3 radios. And remember how we talked about the advantages of giving them different SSIDs so you can connect devices to those different networks. So in this picture, where I have 3 different SSIDs because I have 3 different radios in my tri-radio wireless router, then I can simultaneously connect multiple devices, each one to a different network. If they are all in perfect RF conditions, which typically does not happen, and they all have the equipment necessary to get to these higher data rates, for example, 4 antennas, which most devices don't have, then I can, in theory, get up to 2.1 gigabit per second on 2 of the devices that are operating in the 5 gigahertz band, and in this scenario up to 1 gigabit per second on the device operating in the 2.4 gigahertz band. Now, something to watch out for when you're looking at acquiring a wireless router is there are some routers that when they're marketing their products will actually add the data rates together that you're able to achieve on these independent radios, and then they make some claim that you can achieve over 5 gigabits per second in this particular example by adding them all up. And this can be very confusing for a lot of people buying a wireless router, because they're expecting that they can achieve these really high data rates on their individual device. But it's really a combination of what's theoretically possible on multiple different radios. So do watch out for that. I personally really dislike when vendors aggregate them together and give you an impression that you can achieve much higher data rates. So there's just one more thing I wanted to tell you about when it comes to understanding the data rates that are advertised for your wireless router. So you now understand that the rate that's on the box is your maximum data rate that's achievable with that wireless router, assuming the devices connecting to it is in good RF environment and has all of the advanced features to get to that data rate. Other devices that don't have those features will operate at lower data rates, and devices on the edge of the cell in difficult RF environments will also operate at lower data rates. So depending on where your equipment is in the cell, it's going to experience different data rates. If your equipment is distributed through your home, your average data rate is going to be somewhere in the middle. In this particular illustration, where I have 6 devices operating at different data rates, my average data rate is actually about 670 megabits per second, which is quite a bit below the advertised 2.1 gigabits per second, but is nevertheless still an extremely good data rate. Now, my data rate over the air is different from my throughput, and what users really care about is not the rate at which data is sent over the air. They care about how much of their data did they get across the network. And in Wi-Fi networks, if your neighbor is on the same frequency channel and transmitting at the same time, you're going to wait until they're done before you transmit. You're also going to send control and management information, and that also detracts from your overall throughput. Typically on Wi-Fi networks, your throughput is about half your average data rate. Now, it does vary. In environments where there's lots of wireless routers, your throughput could be a lot less, and in environments where there's not many wireless routers, your throughput could be higher. But typically, if you saw an average data rate of about 670 megabits per second, your actual throughput for meaningful user data would be somewhere closer to 300 megabits per second. Now, when you have bought a product which advertises, oh, I can get to 2 gigabits per second, it can be somewhat disappointing to find out that typically across your cell, you're seeing something like 300 megabits per second in terms of throughput. This often leads to a mismatch between what you were expecting from your wireless router and what you've actually achieved. This is actually the major cause of why people are generally very disappointed when they buy wireless routers with the performance that they're actually able to achieve. This rather sad looking dog here is actually my little old puppy who's waiting for me to finish this recording, so I will take him to the dog park and throw his ball for him. So in this module, you now understand what the data rate means that's on the wireless router products that you've purchased. Hopefully, it's reset your expectations from what you might perceive when you see those very high data rates on the package to what's actually achievable in your wireless network. I really appreciate you watching this module, and I hope you learned a lot. Thank you. In this last module, where we're looking at improving the performance of your Wi-Fi networks in your home or small business, we're going to take a look at the role of extenders, repeaters, and even the potential of replacing your antenna with a higher gain antenna. The most common reason why people look at extenders, repeaters, or high gain antennas is there's regions where they're just not able to get connected to the wireless router, that they're outside of coverage. Now they could deploy another wireless router, but what the people want to do is they just want to extend the range of their existing wireless router. Earlier on in this course, we talked about the benefit of moving to the 5 gigahertz band. It's important to realize that the 5 gigahertz band coverage is going to be less than the coverage that you get at 2.4 gigahertz band. This is simply because signals that are transmitted at higher frequencies attenuate more than signals that are transmitted at lower frequencies, where attenuate means that they lose signal strength, so they simply just don't go as far. And this is important because when you're looking at extenders and repeaters, one of the questions you have to ask yourself is, do I want to extend both the 2.4 and the 5 gigahertz range, or do I have adequate coverage at the 2.4 and I just need to extend the range of my 5 gigahertz signals? Now, the term repeater or extender is used interchangeably, i.e. they're effectively the same thing, and sometimes you might even hear the word a Wi-Fi booster. What they're essentially doing is taking any signals that they hear and then retransmitting them. So you can think of it as receiving a weak signal from your wireless router and then retransmitting it at a higher power level, thereby getting to areas of your home or business that your Wi-Fi signal wouldn't have otherwise reached. Ideally, in this scenario, you'd want your wireless router and your extender to be on different frequency channels. Another scenario that can be used with repeaters is that you use the power lines in your home or business to carry your communications. In this scenario, your main wireless routers would send signals which are heard by the repeater, then sent down the power line to a repeater in another location, perhaps a basement or hard to reach area, which then sends out those signals, and conversely the signals can come the other way, back through the power lines and back to your wireless router, which then provides you the connectivity to your wired network. The advantage of these type of solutions is it's very quick to set up and make work. It's almost a plug and play kind of scenario. The negative aspect, of course, is that you will get a performance hit, which sometimes can be quite significant. All sorts of reasons for the performance hit. One, your power sockets are normally fairly low down, which will impact the coverage and also the data rates that you're able to achieve. And if you're running it through the power lines, then depending on the quality of those cables and the length of those cables, you could see a further deterioration of your signal and therefore even lower data rates. If you decide that you cannot sacrifice performance in the area that you want this coverage, and you're not able to move the existing wireless router without causing other coverage problems, then your only choice is to deploy a second wireless router, which of course is going to be more complex from an implementation perspective. Okay, it's time to talk about antennas. When we think of wireless communications, we're talking about radio waves that are transmitted from our antennas and also received by our antennas. And so when we think about antennas, we can think about them both at the wireless router, but we can also think of them on the client. So for example, if you wanted to connect a laptop or a tablet, you could use an external Wi-Fi adapter as shown here in the bottom right, and you could replace the antennas that it came with, that are shown more in the middle, with a higher gain antennas as shown in the top, or even with directional antennas shown in the bottom left. If you decide, no, I want to look at antennas when it comes to the wireless router, then there's a couple of things that you need to be aware of. Firstly, in Wi-Fi networks, the antennas are passive, i.e. they don't amplify the signal. Let's say, for example, that you're currently using an omnidirectional antenna and it's radiating out, giving you this nice circular pattern. If you change the antennas, you're not changing the amount of energy that's radiated out, you're changing where that energy is radiated to. In this example, you can see that that energy that's radiated out in the circle with an omnidirectional antenna, when I use a directional antenna, it pushes that energy in a specific direction, which means that I can now reach devices that are further away from the wireless router, but it also means that I'm no longer radiating energy in other directions, and therefore there could be devices that I'm now no longer able to communicate with. What you should be taking away from this is antennas change how the energy is radiated out, and you need to make sure when you change your antennas that you're having the right desired effect, because you could find that changing the antennas actually make things worse. Most people today that have wireless routers have either got an 802.11n router or they bought the newer AC router. These routers get up to very high data rates by transmitting from multiple antennas and receiving on multiple antennas. You have to be really careful if you want to replace these antennas. The first thing you need to do is to follow the manufacturer's instructions. You cannot just put any antenna onto these wireless routers. If you do, you could have a significant negative impact on the data rates you're seeing and the overall performance of your network. To show you the complexity that goes into replacing these antennas, I want to just illustrate it by doing a search for the different types of antennas that you might be considering. I'm going into this website by Elcom. I'm not recommending this website, it's just that they have a large display of antennas and I like the look of their web page from an illustration perspective. If we scroll down, you can see they have a number of antennas, many of which don't operate in our Wi-Fi frequency bands, but you can see here they have antennas that work just in the 2.4 gigahertz band. They've got antennas that just work in the 5 gigahertz band, or you can buy antennas that operate in both the 2.4 and the 5 gigahertz band. So that's one of the first questions you have to understand about your wireless router is the antennas that you're replacing, are they single band radio antennas or are they multi-band radio antennas? The next thing to note is if you're deploying 802.11n or AC routers, you're using multiple antennas for transmitting and receiving. Those are what we refer to as MIMO antennas. And so potentially you'll be wanting to replace them not with a single antenna, but with MIMO antennas. If we go into the MIMO antennas, one of the things to immediately note here is that on this antenna here, it has 2 connectors, not 3 or more, which means that if your wireless router is transmitting on 3 or more antennas and you're replacing those antennas, which one has only 2 connectors, then you need to go into the router settings and select the antennas that you want to be transmitting and disable the antennas that you no longer want to transmit. This antenna over on the left has 3 connectors and so is transmitting and receiving on 3 antennas. So understanding your wireless router and what the antennas are doing is very critical for then replacing the antennas, and it may require you to go into your router settings. In many home and small business wireless routers, the ability to change the antenna settings to enable them and disable them is not available. In that situation, I'd strongly recommend that you do not replace the antennas unless you're using a specific antenna that your manufacturer is recommending for your wireless router. The next thing I want to show you, and I'm just going to pick on this dish antenna, what you need to know is how does it change the coverage. And this is a highly directional antenna. Now if I select one of these and scroll down, if we look in downloads, you can see that there is information about this antenna. And what I'm looking for is the radiated pattern. Where is my energy going to go? And if you click on the diagram, it actually displays the antenna pattern for you. And it displays it in the horizontal and vertical path. And most of us think in the horizontal path because that's where we're thinking coverage. And most of us want to minimize the amount of radiation that we're sending in the vertical path, i.e. down towards the ground or up towards the floor above. And you can see that these antennas are pushing the energy in this direction. And so if you had a device that was in this direction, it's now going to be able to connect, but is not pushing energy in this direction. So if you had a device here, it would no longer be able to connect. So these are highly directional antennas. Again, reinforcing that whenever you replace the antennas, you're going to impact where you have coverage, what devices can connect and what devices cannot connect. In Wi-Fi networks are not amplifying the signal, you're just changing where that energy is directed out and over the air. If I have now scared you off from replacing the antennas on your wireless router, I would consider that a success. Most of the problems that I see when I go and help people in their homes or in a small business where they've replaced the antennas are directly related to not understanding exactly how those antennas have impacted the coverage. I've just seen some major disasters in that regard. If you have an area where you think the only way to go is to replace the antennas, then please use the manufacturer's recommended antennas. This finishes up the module on extenders, repeaters, and antennas. What a great way to finish up this course on how to improve your Wi-Fi performance in your home and small business environment. I really enjoyed bringing this information to you. Thank you for watching.